discussions. The next concept that we will discuss is viscosity. First layer of molecules which is interacting with the plate attains the velocity of the plate. This is the so called no slip boundary condition. There are exceptions when this boundary condition may not be valid, but we come into or here we discuss about situations in this particular introductory course where we assume that the no slip boundary condition is valid. Now, when is the no slip boundary condition valid? Let us say that I mean if we magnify a part of this and enlarge it, so you can see surfaces like this. The surface which appears to be flat macroscopically is actually having a large number of ups and downs, and if we have fluid molecules, then these fluid molecules they will be remaining in these asperities or in close contact with the solid boundary, and until and unless the shear force is abnormally large, it is very difficult to dislodge them from the contact with the solid. So, that means if the solid is having a 0 velocity, the fluid will also be having a 0 velocity in contact with the solid. So, the fluid in contact with the solid understands the effect of the wall, and that is known as and if the wall velocity is 0, the fluid velocity is also 0, and that is known as the no slip boundary condition. Now, if we go, let us try to draw the velocity profiles at a given section. So, at the wall the velocity is 0 because of no slip boundary condition. Now, next if we come to the next section which is little bit away from the wall, so the velocity there is not definitely as large as u infinity. Why? Because it still understands the effect of the plate. How does it understand the effect of the plate? It is not in direct contact with the plate. So, how does it understand the effect of the plate? There is actually a messenger, an invisible messenger in the fluid which makes the effect of momentum disturbance propagate through the fluid. The wall creates a momentum disturbance, and this momentum disturbance effect is propagated through the fluid by means of a fluid property, and that fluid property is nothing but viscosity. So, because of the viscous effect, the next layer of fluid which is directly not in contact with the wall also feels the effect of the wall, but implicitly. As you go further away from the wall, you will find that the velocity is even more, but it is still not u infinity till you come to a location where the velocity is almost 99% of almost u infinity, or for all practical purposes is around 99% of u infinity. So, you can see that a velocity profile develops till that location, and beyond that velocity is more or less uniform. Now, so what we can see here is that there is a velocity gradient that is introduced, and this velocity gradient is because of the effect of the wall that is propagated through the outer fluid by means of the fluid property viscosity. So, this is a qualitative understanding of what is viscosity, but remember that viscosity is a fluid property. Therefore, to discuss about viscosity, it is important to relate viscosity with a mathematical equation. Now, when we are planning to do that, let us consider that there is a fluid element whose bottom face is moving with a velocity u and the top face is moving with a velocity u plus delta u. And the height of the fluid element is delta y. Let us assume an unidirectional flow, so that all flow is taking place along positive x direction. So, now let us say that originally the fluid element was rectangular, but because of the differential velocity between the top and the bottom layer, the fluid element is deformed. So, when it is deformed, what is the relative deformation? The relative deformation is that with respect to the bottom, the top layer. So, if we assume the bottom as 0 as an example, because we are interested about the relative deformation, the top layer over a time delta t moves by delta u into delta t relative to the bottom. So, you can see that there is an angular deformation delta theta which is created. Now, from the geometry of the figure, we can say that tan of delta theta is equal to delta u delta t by delta y. This is from the geometry of the figure. If we assume small time delta t, then delta theta is also small and tan of delta theta then may be approximated as delta theta. So, if you take the limit as delta t tends to 0, delta theta divided by delta t this is equal to limit as delta t tends to 0 or delta y tends to 0 for the right hand side. We take a fluid element where the layers are absolutely very close to each other. So, that delta y is 0 tending to 0 delta u by delta y. So, this equation essentially tells what is this? This is theta dot and this is du dy. So, we have got a measure of the angular deformation of the fluid where theta dot is equal to du dy. Now, what is the reason behind this theta dot? There was some shear force which created a relative displacement of the one layer relative to the other, and let that shear force be tau. So, tau is a function of theta dot. Now the question is that what kind of function? What kind of function relates tau with theta dot? So to do that, to understand that, we have to discuss about the constitutive behavior. So theta dot is a kinematic parameter and tau is a kinetic parameter. So the force and deformation, they are related. For a fluid, force is related to the rate of deformation. The reason is that for a fluid, if you quantify deformation, if you allow more and more time, more and more deformation will take place, because fluid is continuously deforming. So for fluid, rate of deformation is what is important. So what we can say is that tau is related to the rate of deformation, which is given by theta dot. So if tau is related to the rate of deformation, then the simplest type of fluid where tau is linearly proportional to the rate of deformation is called as Newtonian fluid, and for that we can write tau is proportional to theta dot. The proportionality constant is known as the viscosity of the fluid. So this is mu, this is the fluid property. So the first important concept that we can understand, that viscosity is defined only for Newtonian fluids. So the fluids which are not Newtonian fluids, viscosity is not defined. You can always define something which is a viscosity like parameter, which may be considered as apparent viscosity or effective viscosity, but when you are talking about viscosity, viscosity is defined only for Newtonian fluids. This is the first concept. The second concept is that the dimension of viscosity, when you talk about, you can discuss or you can bring out the dimension of viscosity by dividing the dimension of tau with dimension of theta dot. Now I will not bring that out here because it is too trivial, and if you do that, so dimension of mu is dimension of tau by dimension of theta dot. So this is m L to the power minus 1 T to the power minus 1. So I hope that the concept of viscosity is clear. We again try to iterate that physically it is the messenger of momentum disturbance in a fluid. So if there is a momentum disturbance at a point in the fluid, there is a fluid property that understands that yes, there is a disturbance and I should propagate the effect of this disturbance to the outer fluid, and that is done with the help of the fluid property viscosity. Now related to the fluid property viscosity, there is another property which is called as kinematic viscosity. Kinematic viscosity is defined as nu is equal to mu by rho, where rho is the density. So what we can say is that mu by rho, if you work out the dimensions, you will see that it is like in SI unit, its dimension is meter square per second. So that means that it is a kinematic parameter, it does not include the unit of mass. So, that is a straightforward interpretation, but what is the importance of this property? Many times for fluids we use the kinematic viscosity as a property instead of the viscosity as a property for assessing the flow behavior. Why do we do this? Now you see mu is an indicator of what? Mu is an indicator of the propagation of the disturbance in the fluid, and rho is an indicator of the ability to sustain momentum, because rho is related to mass and mass is a measure of inertia. So, with rho what it means is that the rho, higher the rho, larger is the ability of the fluid to maintain its momentum, and mu is the ability to create a disturbance in momentum. So, it is the relative ability of the fluid to create a disturbance in the momentum with respect to the sustenance of the momentum, that is given by the property kinematic viscosity. So, that is the physical significance of the parameter kinematic viscosity. Now, the next physical concept that we will try to learn is that what is the origin of this viscosity, or what are the important parameters on which the viscosity depends. So, when we are doing that, let us consider the cases of gases and liquids differently. New page. Gas. So, let us say that you have some gas molecules moving with a velocity u, and you have gas molecules moving with a velocity u plus delta u. So, the upper layer of molecules are faster moving molecules and the bottom layer of molecules, these molecules are slower moving molecules. Now, what happens is that these gas molecules are under continuous random motion. So, because of this random motion, there is a possibility that the bottom layer of molecules joins the top layer and slows down its momentum. Similarly, the top layer of molecules joins the bottom layer and slows down and enhances the momentum. So, it is possible, let us say that you have a group of friends. Now, suddenly you find that there is a friend who is sort of sleepy and sluggish type. So, it will reduce the momentum of your group significantly. But if you have a friend joining who is very dynamic, a friend joining your group who is very dynamic, then that dynamism will be reflected in the behavior of your group. So, individual entities which have a higher momentum will try to enhance the momentum of the group, and individual entities which will have lower momentum will try to slow down the momentum. So, in this way there is a transfer or exchange of molecular momentum. So, that is the origin of viscosity of gases. Remember that for gases intermolecular forces of attraction are not that strong. So, intermolecular forces of attraction do not dominate, but transfer of molecular momentum or exchange of molecular momentum dominates. For liquids, on the other hand, the viscosity is primarily because of intermolecular force of attraction, because intermolecular force of attraction is a dominant force for dictating the viscosity of a liquid. Now, can you say that given this origin or mechanism of viscosity in gases and liquids, if you increase the temperature, what you intuitively expect? Do you intuitively expect the viscosity of the gas to increase or decrease, or liquid to increase or decrease? Let us try to answer this question. If we increase the temperature of the gas, then there will be more vigorous molecular momentum exchange between the layers, because the molecules will be having more vigorous vibration, their kinetic energy is a function of the temperature. So, there will be more viscosity. On the other hand, for liquids, if there is more temperature, there will be less intermolecular force of attraction, and that will reduce the viscosity. So, higher temperature for liquids commonly means that there is a reduction in viscosity, whereas higher temperature in gas will imply a higher viscosity. The other important concept that we want to discuss before bringing out a closer to the concept of viscosity is that there are different types of fluids which actually do not obey the Newton's law of viscosity. So, if you plot the tau versus theta dot, tau is linearly proportional to theta dot, so that is called as Newtonian fluid, and the Newton's law of viscosity, that is tau equal to mu into theta dot, that is the Newton's law of viscosity. That Newton's law of viscosity is valid only for a Newtonian fluid, but there are other types of fluids, like you can have a non-linear variation of viscosity, and non-linear variation of viscosity may be several types. Even there can be a linear variation of viscosity, but with a shift, with an yield stress. So, these different types of fluids are not Newtonian fluids, and their behavior can be attributed to like their peculiar behavior, peculiar rheological characteristics, and it is beyond the scope of these few lectures to talk about that, but I would suggest the interested readers to look into the books on rheology or non-Newtonian fluids to get feel on the behavior of these types of fluids. So, to summarize what we have learned regarding viscosity, that what is the origin of viscosity, what is the mechanism behind viscosity, what is kinematic viscosity, and what is its significance. So, with this introduction on viscosity, next we will try to learn a new a different concept which is related to another fluid property, which is called as surface tension. Surface tension. Let us say that there is a container, this container has some liquid and some vapor at the top of this liquid. Now let us consider a molecule which is in the liquid. So if you have a molecule in the liquid which is like this molecule will be acted upon by forces equally from all sides. Because of that the molecule can be in equilibrium. Now let us say that there is a molecule at the interface. It is obvious that the pools on the molecule will be different from the vapor side and in the liquid side. In the liquid side, because of a greater density of the molecules, it is intuitive to expect that the force from the liquid side is much stronger than the force from the vapor side, and the reason is obvious. The reason is that the density of the liquid side is much more compact as compared to that on the vapor side. So the molecule at the interface will have a tendency to get dissolved in the liquid, but in actuality it does not do so. So that means molecules at the interface have some excess energy by virtue of which they retain their position at the interface and do not get dissolved in the liquid despite having a stronger force from the liquid side than the vapor side. This additional energy is called as surface energy, and the corresponding force per unit length is called as surface force. Why there is a corresponding force? Because of this tendency of the liquid of the interfacial molecule to get dissolved in the liquid, the molecules at the interface appear to be in some kind of tension. Because they appear to be in some kind of tension, we say that it is a manifestation, it is culminated in the form of a force which is normally expressed as a force per unit length, and this force is known as surface tension force. So the unit of surface tension force in SI units is Newton per meter. So with this understanding of surface tension force, let us now try to see that what are the consequences of this surface tension force. One of the important consequences of this surface tension force is to create a pressure difference across the two sides of an interface, and next we will learn what is the pressure difference across two sides of an interface because of surface tension. So let us look into this view graph where there is a membrane. You can see this membrane has a dimension of x along one side and y along the other side. So the area of this membrane is x into y. Now there is a pressure difference across the two sides of the membrane, and the membrane stretches and comes to a new configuration. In the new configuration, the dimension of the membrane, the x becomes x plus delta x and y becomes y plus delta y. So there is a work done because of pressure, and the work done because of pressure is given by delta p into the change in volume. So or we can say that delta p into xy is the area. So the delta p is delta p into x into y is the force acting on this surface times the displacement delta z. So, the force times displacement is the work. So, delta p into x into y is the force times delta z is the displacement. So, that is the work done. So, the work done by the pressure is equal to the work done by the surface tension. So, what is the work done, because by the surface tension you see that more surface is created from a surface area of x into y, the surface area that is created is x plus delta x into y plus delta y. So, a new surface area created, that is x plus delta x into y plus delta y minus x into y, that is the additional surface area that is created. And when this additional surface area is created, there is a work associated with that. That work, if this additional area is delta A, then that work is sigma into delta A, where sigma is the surface tension coefficient which is the force per unit length that we described. So, the surface tension coefficient is also very commonly or loosely termed as surface tension. Surface tension and surface tension coefficient many times indicate the same fluid properties. So, we can write if we equate this work and energy, we can write delta p into delta x delta p into x y into delta z is equal to sigma into delta A, where delta A is x plus delta x into y plus delta y minus x y. So, that becomes x into delta y plus y into delta x, that is what is written here. Of course, we neglect the term delta x into delta y, that is small. Now, we can relate delta x, delta y and delta z with the radius of curvature of the curved faces x and y. Let r1 and r2 be the radius of curvatures of these sides. So, from similar triangle concept we can write r1 by r1 plus delta z is equal to x divided by x plus delta x. So, r1 becomes delta z by x plus delta x. Similarly, r2 becomes delta z into y by delta y. So, in place of delta z into x by delta x, we replace r1, and similarly we replace r2. So, in the work energy expression, if we write the work energy expression in terms of r1 and r2, we can write delta p is equal to sigma into 1 by r1 plus 1 by r2. This is a very important equation, and this equation is known as Young-Laplace equation. Now, let us consider two examples. One is a spherical droplet and another is a spherical bubble. Now, if we have a spherical droplet, for a sphere all the radii of curvature are the same. So, r1 is equal to r2 is equal to r, and therefore, we have delta p is equal to 2 sigma by r. On the other hand, for a bubble which has two interfaces, one inside interface and another outside interface, for each interface we have a pressure drop of 2 sigma by r. So, the total pressure drop across the inside and outside of the bubble is 4 sigma by r. So, it depends on whether we are talking about two interfaces or a single interface. So far we have understood what is the surface tension force, how is it expressed, and how does it manifest in terms of a pressure difference. Okay. Next we will try to understand that you have now the two sides of the interface. So, out of the two sides of the interface, which side of the interface has greater pressure, the concave side or the convex side? We will try to develop a qualitative understanding for that. Let us say that we have an interface like this. So, how does the surface tension act? The surface tension acts tangentially like this. So, you have a pressure from this side, let us say this is P out, and a pressure from this side say P in. In or out is just arbitrary, it depends on this is P out. So, in and out depends on from which side we are looking at. So, this is I am just calling this as out and this as in. Now, you can see that qualitatively P out plus a component of surface tension, because of this will have its components downwards like this. P out plus surface tension, I mean pressure due to surface tension is equal to P in. So, Pi minus Po is greater than 0. That means, when we say that delta P is equal to sigma into 1 by R1 plus 1 by R2, we have to understand that this out of that, I mean in that expression for delta P, Pi is greater than P0. Now, there are many natural phenomena which occur because of surface tension, and we will describe about one such phenomenon which is called as capillary rise. So, if you look into tall trees, it is actually a very common phenomenon, but it is very surprising that the trees have no pump, but although trees have no pump, water that is sucked from the ground reaches the tallest branches, topmost branches. So, it moves against the gravity and there is no pump. This is called as ascent of sap. Now, how does ascent of sap takes place? How does this water which is taken from the ground moves to the distant branches and supplies nutrition to those branches? So, that is possible by a phenomenon called as capillary rise. Capillary rise. So, let us say that we have a tube, capillary tube. I am just drawing it thick, but it is not thick, it is thin and it is immersed in a liquid bath. Now, when we say capillary rise, it is a misnomer because it can also be a capillary fall depending on something which is called as contact angle. So, we will describe what is a contact angle. Now, let us say that you have an interface here, and when this capillary is dipped in this bath, the fluid gets displaced and moves up by an average height of h. Now, it is clear. So, let us use our previous notation. This is PO, this is PI. What is the pressure at this surface? This is also PO because the atmospheric pressure acts here. So, here the atmospheric pressure is there, here the atmospheric pressure is there. That means, if you consider the liquid, this is the liquid if you consider the liquid, then you can say that delta P is equal to P I minus P O, and that is nothing but H into rho into G. This you know from high school physics. Now, delta P again by the Young Laplace equation, that is equal to sigma into 1 by R 1 plus 1 by R 2. Now, what is R 1 and R 2? It depends on the shape of the meniscus that we are talking about. So, if we consider the meniscus to be part of a sphere, that is this one to be a spherical cap, then R 1 and R 2 both are same, and that is same as the radius of the sphere of which it is a part. It is very important to distinguish here that the radius of the sphere of which this is a part is not same as the radius of the tube. So, let us say that the radius of the tube is small r, and radius of the sphere of which this meniscus is a part, imaginary sphere of which this meniscus is a part, let us say that is capital R. So, this is 2 sigma by capital R. Now, we have to relate capital R with small r. So, to relate capital R with small r, what we do is we make a simple geometrical construction. We draw the tangent to the interface, and that makes an angle theta with this contact line. This angle theta is known as contact angle. Now, what we do next is we draw a normal, maybe I draw a distinct figure to distinguish that. So, we have angle theta, we draw a normal, and this normal cuts the center line at some location. So, this angle is theta, because this total angle is 90 degree, this angle which I am showing here, this angle, this is 90 degree minus theta, and therefore, if you complete this triangle, this angle is theta. Remember that this is capital R and this is what is small r. Small r is the radius of the tube and capital R is the radius of curvature of the interface. So, we can write small r is equal to capital R cos theta. So, we can write delta P is equal to H rho G is equal to 2 sigma, in place of this R 2 sigma, then in place of this R capital R we will replace small r by cos theta. So, 2 sigma cos theta by small r. Okay. So, what it means is that H, let us write a formula for H. H equal to 2 sigma cos theta by rho g r. Now, let us try to analyze this formula. If we are trying to analyze this formula, we have to keep certain points into consideration. First point, is H is proportional to 1 by R. Okay. So, what we can see is that H will be larger and larger as R becomes smaller and smaller, and that is why you will see that this phenomenon for capillary displacement, no matter whether it is rise or fall, this phenomenon is more apparent when the dimension of the capillary is smaller and smaller, because when the dimension of the capillary is smaller and smaller, then only you will have a significant H. So, if you consider a flow of water through a pipe, you will see that H, if it is if the pipe is of the order of meters, the H will be very small, but if the pipe radius is of the order of microns, which is called as micro capillary, then H is significantly important. So, we can say that H, the relationship between H and R, is very important for designing the capillarity phenomenon. The other important issue is the contact angle theta. So, smaller and smaller the theta, larger and larger is cos theta, and then larger and larger is H, and if cos theta is negative or cosine of the contact angle is negative, then you can see that H will become negative. So, instead of a rise, it will be a fall, and that phenomenon is known as capillary depression. So, to summarize, what we can say is that we have discussed about two important fluid properties, which are viscosity and surface tension. So, these two properties are very important, and other than these two properties, we will discuss about another important property now, which is the density of the fluid, which we have discussed loosely, which we have introduced loosely, but we will discuss about the density of the fluid in a more formal way. So, density. So, essentially we are discussing about various properties of the fluid. We have discussed about the concept of stress, but we have not discussed about the concept of pressure to be specific, because it will be discussed in details in the chapter of fluid statics tomorrow. We have discussed about viscosity, we have discussed about kinematic viscosity, and we have discussed about surface tension. So, next we will discuss about density. There is a question? Okay, let us take a question before we get into density.
RCID 1217. Do you have any question? RCID 1217.
Hello, can you listen, sir?
Yes, yes.
Hello, sir. I have a question.
Yeah, yeah. Please go ahead.
Sir, the applications of surface tension, sir. We could understand the fundamentals behind the surface tension. Can you please explain some applications of surface tension?
Okay.
One or two.
Okay. So, one example I have already given is like how water is transported from the ground to the tallest branches of the trees. Like if you see that capillary rise phenomenon. So, this capillary rise phenomenon, the height by which the fluid will rise will be inversely proportional to the radius of the tube. So, if the radius of the tube becomes smaller and smaller, then there can be a significant rise. So, without having any external pump, just by utilizing surface tension force, naturally you can pump water. So, you do not require pump, that is one example. The other example is you can form droplets. So, you can form bubbles, all these are formed in nature because of surface tension. So, you can essentially deal with droplets, bubbles and interfaces, and any practical example that deals with droplets or bubbles or interfaces, their surface tension is inevitably involved. Okay. Okay, so we move on to the concept of density. So, we know that the density as a fluid property we loosely say as mass per unit volume. So, you have let us say now the question is, so this is a very gross concept or gross understanding. Question is, what is this volume that we should choose? So, now if you make a plot of density versus volume delta V, then what is the delta V that you should choose? If you take a very small delta V, you will see that the density is fluctuating like this, then it comes to a constant and then beyond that it varies like this. So, if we take a very small volume and then calculate the mass within that and find the mass divided by volume, then we are within the statistical uncertainties because of the presence of only a few number of molecules. But if we go to a volume which is beyond delta V star, then beyond this delta V star we see that their fluctuation is less, but beyond a certain volume we see that because of the variation of local density and as we have come to a different point we are coming with a different velocity, a different density. Therefore, the choice of the elemental volume delta V should be very judicious. It should not be so small that continuum hypothesis is violated. So, there should be a critical volume delta V star, but it should not be too large so that you are not able to capture point to point variations and you are getting an average. So, we have discussed about the property density, and the final concepts which are left in this particular chapter, which Professor Som will now discuss, will be based on compressibility issues. But before coming into that, there is some question and we will address that question. One 3 1 0. 1310. Please go ahead with your question if you have question. Center 1310.
Hello,
Yes,
I am talking from 1230.
yes, please go ahead.
Hello.
Yes, you are audible.
Participants here.
Yes,
They have asked what is the practical application of kinematic viscosity.
okay. Practical application, let me give you a very I mean practical example. All of you know molten steel as a fluid, right, and you know water as a fluid. So, can you tell which is more viscous, water or steel? Are you online? Are you online? Yeah, can you tell which is more viscous, water or steel?
Water or
Water or steel, molten steel, which is more viscous?
molten steel.
Molten steel is more viscous, right. So, it may have viscosity significantly larger than that of water, even from common sense we can say. Which has more density, molten steel or water? Which has more density, steel or water? Steel. So, mu by rho, interestingly the kinematic viscosity for water and steel are the same or almost the same, not exactly the same but virtually the same. Mu of steel is much more than mu of water, rho of steel is much more than rho of water, but mu by rho wise their values are very similar. That means ability of the fluid to entertain a momentum disturbance with respect to its ability to sustain its own momentum is same, almost the same for water and steel. That means kinematically in terms of responding to a particular disturbance, fluid molten steel and water in terms of kinematic viscosity they will behave almost similarly. So, in steel plants, if you are looking for a practical example, so if you are visiting steel plants, you will find that it is very difficult to do experiments with hot molten steel and they are doing experiments with water model. Of course, heat transfer wise water and steel are very much different because their thermal diffusivities are strongly different, but in terms of fluid mechanics because of the mu by rho of water and steel are very similar, many times by doing experiments on flow visualization on water based models, people in steel plant predict that what could be the similar related phenomenon when the experiment is done with steel, and that helps in optimizing the steel making processes, because it is very difficult to do such flow visualization experiment with molten steel, because molten steel as you know is not transparent and it is too hot to handle. So, this is one of the practical applications where by looking into the similarity of kinematic viscosity, experiment with water is extrapolated towards predicting the behavior of something which is not as transparent and as easy to handle as water. Okay, I think we will hand it over to Professor Som for concluding this particular session on fluid properties, and Professor Som will now discuss about the compressibility issues, and thereafter we will take a tea break and we will take more questions.